You decide. I'm just... James Webb is in fact designed to work in infrared, and because of the expansion of the universe, the faraway galaxies are actually all in infrared. So all the light coming to us is actually in infrared. So very much by design, James Webb was going to show us the very first generation of galaxies. And basically without it, we won't be able to see it. But as always, just like Hubble was built to do specific things, yes, it did those, but then over 20 years has done unbelievable. I think there's about 10 or 15,000 papers written with Hubble, and it's just, you know, Hubble fellowships, that's good. But it's really, it's one of, you have it and suddenly people find all the different ways to do it. Again, so James Webb will be expensive initially, people will, you know, do certain things with it, but I'm sure, you know, if you have a tool like that for 20 years, and people will use it in many different ways we don't even imagine at this point.
Is it 2018 now?
I think it's, basically it moves away by every year. So, you know, 2 years ago was 2015. Basically at this point my understanding is NASA has no money and the Congress is not willing to give it any money, but it hasn't killed it. So basically that means it's just kind of moving away into the future where we somehow will find money. By cutting taxes, of course. Okay, I'm in Kentucky, I know. I'm kidding. Yes, sir.
How does dark energy, dark matter, and all that fit into this?
So dark energy is what, to our understanding, makes the universe now accelerate. We need something in the universe that behaves differently than gravity. Dark matter has gravity like just ordinary matter, except we don't see it because it doesn't produce any photons. That's 23% of the universe. The remaining 72% of the universe, 75%, is the dark energy, and the stuff we are made of is 3%. So we're represented. But, you know, really, you know, if there was a two-party system, we wouldn't be represented. No, I'm sorry. There's a debate tonight, that's why you know, so we are 3% of the universe right now. It used to be in the universe, if you go back, the dark energy business was completely negligible because the universe was tiny. So there was no space in it. So the dark energy sector, if you will, grows with time just because the universe grows. The dark matter basically was dominating the universe. We are always a small fraction of the total energy budget or mass budget. What the dark energy is, nobody knows. We know it's there, it's very well established, that's why they gave the Nobel Prize, but what actually physically makes the universe accelerate, nobody knows. There's probably hundreds of papers written proposing different ideas, but we don't have the answer. Dark matter is the same story. We have discovered basically that it's there, because we basically see much more gravity that we can account for with the stuff that we know. For example, if you look at clusters of galaxies, the galaxies in clusters move way too fast. In order, you know, we couldn't explain how fast they move if we just counted the atoms in the galaxies. And so there is 10 times as much dark energy as there's what we call baryonic matter, the stuff we are made of. But again, we don't know what it is. I hope that within 10 years or so, I don't think astronomers actually answer that question. This probably will come from either particle physics or, you know, completely new idea. But people are very much trying. It's just, you know, we just don't know. But the 3% we know pretty well. Yes?
Is there any idea or evidence that there are other universes?
Sure. So there are many papers and there are many ideas that, you know, because people have a hard time, you know, how come this universe just sort of happened, that if there are, you know, many universes being born and dying, and only some of them will be successful in the sense that, you know, you could find yourself being an observer in them. My problem, I am an observer. I take data, analyze the data, publish a paper. This other universes, until somebody else figures out how to do it, there is no data. So, you know, for me, it's philosophy.
There could be universes that are kind of interfering with this universe.
Sure, but, you know, unless we actually find a way to show that, for me, that's kind of, it's interesting, but it's something you read, you know, in the afternoon while having coffee. No, I mean, some people make a career out of it, but I'm an observer. I want data. I want to be able to observe it and, you know, analyze it. Otherwise, it's really not science. Very much science, part of the scientific process is you have a hypothesis, you propose certain observation, either survives and then becomes a theory, which is a good thing, or it dies and then, you know, it wasn't a good hypothesis.
I asked if there was any evidence.
No, really isn't. Yes.
We have time for one more question, and then after that we can have a couple more questions, and then after that we can retreat to the rotunda for some refreshments.
Sir. So it's not. So the solar system, basically the lambda really kicks in on very large scales. Locally, the solar system is completely dominated by the sun. So lambda only matters because there is so much empty space in the universe. That's that's the best I can do. This dark energy thing is directly proportional to how much space I have. There is very little space in the solar system compared to the universe. So locally, the evolution of the orbits are all dominated by the fact that the sun sits there, and then planets can perturb each other. But lambda completely dominates the universe once I take the whole universe, because the universe mostly is empty space. And now we understand, again, we don't actually understand how this happens, but we understand that when I have empty space, the lambda term or something else kicks in and makes the universe accelerate. Yes, sir. Yes. So as I was mentioning, he initially introduced it to make the universe stable. It turns out that was his mistake. It wasn't introducing lambda that was his mistake. He didn't understand at the time, stability is harder to study, that even if you have lambda, the universe actually wouldn't be static. So even with lambda, either accelerates or shrinks again. And so he kind of called it his biggest blunder, but that's in some ways correct, because he didn't really appreciate that even with lambda, it wasn't what he thought it would do, namely it wouldn't make the universe static. There was... So this is what we mean by this redshift thing. Basically, when I look about half of the age of the universe was expanding only half as fast. So, galaxies were 2 times closer to me, but the Hubble law was still applying. It's just the Hubble constant actually, it's not the constant of time, it's constant at any given time in the universe. So the universe is expanding faster and faster and faster. And on top of that, any two galaxies are moving away faster, and now we actually understand that also there is acceleration in there. Sorry, there was a question. Yes, sir.
This is to your studies at Ohio State. In your studies, where do you get your data from? Do you all have research facilities there, telescopes?
So we have the LBT. That's really by far the most expensive. It's a very expensive way to get data, but it also, you get data you couldn't get otherwise. But the great news about Hubble Space Telescope, Chandra in X-rays, all of these data become public. So quite a few papers I've written is actually, you wait a year, somebody proposed to get data, but either they haven't done something, or they have, all the data becomes public. So it's a very good mixture of big telescopes, small telescopes, and also telescopes in space.
Do you ever make the change yourself to go out personally?
Well, sure. When I was a postdoc and before I had kids, I would spend roughly 3 months a year observing on the mountain. That gets old very quick. You get nosebleeds, it's very dry. At 14,000 feet, it's, you get headaches all the time. But you do it because nobody else will do it for you. But now I have graduate students, so life is good. just kidding.
I think maybe what the previous person was asking was the acceleration of the expansion of the universe. So we learned about the procedure and methodology of measuring distance scales, and
so
from that the redshift, the expansion as a function of distance, but the actual, not only the expansion, but the acceleration of the expansion.
So I didn't talk about it because, again, that's kind of almost a separate talk. This is where people use supernovae as a standard candle, and they measure their brightness as a function of distance from us. So they can actually see that the universe, they can actually measure their recession velocity, and they at the same time can measure the distance. So they can actually, then they see deviations from the simple Hubble law, namely the universe in the past was expanding slower because it's accelerating now. If I go really even farther away, then it turns out the universe was actually slowing down as well because the lambda didn't kick in yet. So if I go to what we call redshift 1 or so, this is when the universe was half of the size. The universe was actually slowing down, but already was becoming big enough that the lambda was kicking in. And now lambda is about 75% of the universe by energy. If you wait long enough, lambda becomes basically everything is lambda.
So gravity was kind of slowing down the
Yes.
expansion, but it didn't quite make it.
It didn't just make, and it's kind of, people always say, how come they're kind of about the same? We have no idea. We just don't know. I mean, it's as I always, we have this morning coffee at OSU every day, discuss papers. I say science is a process. We learn things and we're often wrong. I mean, it's just, that's part of the job. I mean, we don't want to be wrong. Nobody wants to be wrong, but it's just, and this dark energy business, people really, you know, not just Nobel Prize. I mean, it's $1 million. I mean, it's a good thing, but it's not. Really, it's, you know, if you solve this, you'll be next Newton, or something like that. So.
We have time for one more question, then we can exit toward the rotunda for refreshments.
My question is about the creation of space itself. Is that basically from the inflationary period? Because
So we're not in inflation anymore. So if you write GR, the whole universe is expanding. So it's not expanding into anything. It's the distance between any two objects increases with time. So if you will, space grows. I mean, mathematically it's easy. I mean, I can just write down the equation and two objects their distance will be increasing.
Well, the reason I ask is because in string theory, Calabi-Yau shape is what we determine 3 dimensions that unfurl to infinity, and then we have the 6 curled up dimensions. And that's what we use in order to determine our 4-dimensional universe.
Sure.
But
So yeah.